This video is going to introduce you to two fundamental decompositions and how to use them in the context of principal components analysis and dimensionality reduction. So we've been talking about principal components analysis, and what principal components analysis does is it takes a scatter plot, and what it tries to do is find a new set of axes. Okay, so it's going to choose a new axis called the first principal axis that is in the direction of the most variance in the data. Okay, so the most variance in this particular picture is in this direction. Therefore, the first new axis is going to be this 45-degree line. The second axis with principal components analysis is the dimension that captures the second most variance and is orthogonal to previous axes. In this case, we only have one previous axis. So this would be our second principal axis. Now, what I told you during lecture last week was the first axis is given by the first eigenvector of the X transpose X matrix, so the covariance or the correlation matrix, depending on whether you standardize your data. And the variance in this direction is given by the first eigenvalue. Then the second principal axis is described by the second eigenvector of the covariance or correlation matrix, and the variance in this direction is the second eigenvalue. And I said, just trust me, these eigenvalues, eigenvectors exist. What I want to do in this lecture is to give you some background on eigenvalues and eigenvectors and try to build up your intuition. All right, so let's go back to the slide where I actually define this stuff. So this is meant to be a review of linear algebra. And so, I'm going to go fast. You should go back to a linear algebra book for a more thorough treatment. But this kind of hits the main points we need for principal components analysis. So back in linear algebra, you would have studied a P by P matrix, and it would have been called A most likely. And then you got a definition back then saying that a number, so this is a scalar number, lambda, is an eigenvalue with some corresponding eigenvector, gamma, if and only if this matrix times the eigenvector is in the same direction as that eigenvector scaled by the eigenvalue. Now, quickly after that, the first result that you would have encountered in your linear algebra class is that the definition is equivalent to this system of equations, or this equation right here. So the determinant of this A matrix minus lambda times I has to equal 0. All right, now this is going to produce a polynomial in degree p, in lambda. All right, so I'm going to illustrate this in a minute with an example. So just hold on. The way we've been writing our eigenvalues and eigenvectors is, our eigenvalues, there's going to be p of these. So we'll just store those in a matrix, a diagonal matrix, capital lambda. And then this matrix gamma is a P by P matrix of eigenvectors, where the columns are the different eigenvectors. And without loss of generality, we always order this in descending order of our eigenvalues. So the largest eigenvalue will always come first. The smallest eigenvalue will always be last. Now, I mentioned that this is going to be about two really famous decomposition theorems. So the first one is called the eigendecomposition theorem, and it says this, that any symmetric matrix, so in our case, we're going to be dealing with covariance and correlation matrices, both of which are symmetric. So the correlation between x1 and x2 is the same as the correlation of x2 to x1, therefore it's symmetric. And what this eigendecomposition theorem says is that any symmetric matrix can be written as a product of its eigenvalues and eigenvectors as follows. All right, so the only other thing to note is that these eigenvectors, I'm going to assume are orthonormal. Of course, they're going to be orthonormal. We constructed them that way. They're constructed that way, but they all have length 1. All right. So where I'd really like to illustrate this is with this your term. So I've given the simplest correlation matrix here. I've got two variables, x1 and x2 column, and I've standardized both the variables. So the variance of any individual variable is 1. Variance of x1 is 1. Variance of x2 is 1. The correlation between them is rho. All right, and so we've been told to find and interpret the eigenvalues and eigenvectors of this matrix. So let's go over here, and I've kind of worked this out. Ordinarily, I would do this on the chalkboard. So how do we find the eigenvalues and eigenvectors? Well, let's go back to that result that I gave you. What I just told you was that a scalar lambda is an eigenvalue if we solve this equation. So the determinant of this matrix, my symmetric matrix, minus lambda I, if you take the determinant of that, it has to equal 0. So let's go fill stuff in. So I'm going to take, here's my sigma matrix, minus lambda times the identity gives me this matrix right here. All right. Now, if you remember how to compute a determinant, we take this term times this term, so 1 minus lambda squared, minus rho squared. All that has to be 0. So if you move your lambda, your rho squared over to the other side, take the square root, what you'll find is that you have two eigenvalues. The eigenvalues are 1 plus or minus rho. And so those are the eigenvalues. Well, now let's go find the eigenvectors. So to find the eigenvectors, we're going to go back to the definition that I gave you. So if we take the matrix times the eigenvector, we have to get some multiple of the eigenvector, and the multiple is the eigenvalue times it. So I'm going to start out with one of my eigenvalues, and I happen to choose the eigenvalue 1 plus rho. So let's go use this definition. So if we let gamma equal the vector of two scalars, gamma 1, gamma 2. If we take sigma times gamma, we get 1 plus the rho, so that's my eigenvalue times that vector, and I'm going to multiply it out. And notice we get a system of two equations in two unknowns. But if we look at this, okay, so gamma 1, oops, this is there should be a plus sign there. I'll fix this before I send it out to you. So gamma 1 plus rho times gamma 2 has to be gamma 1 plus rho times gamma 1. Then likewise, there should be a plus sign down here. So rho gamma 1, so take this times this, plus gamma 2 has to equal gamma 2 plus rho gamma 2. Now the only time that the system of equations will work out is when gamma 1 is exactly equal to gamma 2. All right, so what that tells us is any vector in this direction where gamma 1 is equal to gamma 2 is an eigenvector associated with this eigenvalue. So what are some example eigenvectors? Well, one possibility would be the vector 1, 1. Now the problem with 1, 1 is that it's not unit length, but we could fix that by simply dividing by the square root of 2, the length of that vector. And so this would be another eigenvector. Another eigenvector would be minus 1, minus 1. So just have it pointing in the other direction. So those would all be eigenvectors associated with this eigenvalue. So they're not unique. Now, I'm going to leave as an exercise the other eigenvalue. So the other eigenvalue was 1 minus rho. And so an eigenvector is any multiple of this vector. So 1 minus 1 So if you multiplied this by -1, you'd get -1 comma +1. That would also be an eigenvector in that same direction. You could divide by the square root of 2. You could do whatever you want. All right. Now, we've also been asked to interpret the solution. So let's go do that. So what I said here is that the eigenvector associated with 1 plus rho is 1, 1, which is this direction. So that's our first principal axis. And our second principal axis is going to be pointed in this direction. So 1 minus 1 would be our second eigenvector. And again, there's an infinite number of eigenvectors that describe each one of those axes. Now, let's just pick some positive correlation. So let's say rho is a half. And if I set rho to a half, then the first eigenvector is going to be 1 plus a half, and the second eigenvector is going to be 1 minus a half. And so the point I want to make with this is there is more variance in this direction than in this direction. And that's kind of indicated by this ellipsoid, which would be this ellipse, which would be describing the joint distribution between x1 and x2. Now, another thing we said was we often compute the fraction of variation in any direction. Well, the total of my eigenvalues is 2. Now that's because the sum of the diagonals here, so I have the variance of x1 is 1, the variance of x2 is 1, so there's a total variance of 2 in the data. All right, so the sum of the eigenvalues equals 2. What we can say is 3/4 or 75% of the variance in this data set goes in this direction. Only 1/4 of the variance is in this direction. All right, so with the original variables, with x1, the variance in this direction was 1, the variance in this direction was 1. But by changing these axes, we've identified a new dimension where most of the variance takes place. And so how much variance? Well, 1.5. Let's go try another problem. So let's say we made rho minus a half. All right, so then this first eigenvalue, I know I told you to order them a minute ago, but allow me to use the notation. This is going to be the first eigenvalue corresponding to this direction. All right, so if we take 1 minus 0.05, we get 0.05, 0.5 I mean, and if the other eigenvalue is going to be 1 minus a minus 0.5, which is 1.5. All right, so again, what this is saying is the variance along the second direction is 1.5. The variance in this first direction is only a half. This is 3/4 of what's going on in the plot. This is 1/4. All right, just for another example, let's take rho equal to 0. So if rho is equal to 0, we have kind of a circular set of contours. There is no association between the variables. In that case, oops, this is another typo. This should be lambda 1 equals lambda 2 equals 1. I'll fix that before I send it out to you. All right, so what that's saying is the variance in this direction is 1. The variance in this direction is 1. As with the original variables. So principal components analysis doesn't help us at all in this case where our correlation is 0. There's just no way to really reduce the dimension of that data set. The more correlated the data, the more you can capture with a principal component. All right, I'd like to do one more thing with this kind of toy example that we have here. So the Eigen decomposition theorem said that we can take any matrix and any symmetric matrix and write it as a product of the eigenvectors and eigenvalues. So let's go just try that. So I'm going to go take gamma. Now, there's one small catch. The small catch is that here we're going to make sure we have unit length eigenvectors. So this is going to be my gamma matrix, and to make them have unit length, we'll divide by 1 over the square root of 2. So think of this piece right here as our first gamma matrix. What is my set of eigenvalues? So the lambda matrix. Well, here's that lambda matrix. 1 plus row, 1 minus row in the diagonal. It's a diagonal matrix, so there's zeros off the diagonal. And then we need gamma transpose. Well, how do we transpose this matrix? That's easy. It's the same matrix since the off-diagonal elements are the same. So this is the transpose. Now, I didn't work out the details. I'm going to leave that for you. But if you compute this two matrix products, so it's going to be slightly tedious, what you're going to find is that sure enough, we have recovered the original sigma matrix. All right, so I'm going to leave that as a little exercise for you. Now, what's very useful about this, another way to kind of think about what's useful beyond just finding the dimension where most of the variance is taking place, is that we're going to use this to approximate our covariance or correlation matrix. So just to illustrate this, let's go back to the grizzly bear data set, which I hope that you've tried on your own. So remember, I gave you 6 measurements on a bunch of grizzly bears, gave you the correlation matrix, the covariance matrix. We can compute this to a correlation matrix with the cub-to-core function. So we were using this back when we were talking about Gaussian mixtures. And so let's just go print out the correlation matrix. Here's our correlation matrix. All right, now I'm going to go find the eigen decomposition. So we can do that in R with the function eigen. And if you want to see what that looks like, eigen returns a list with a vector of values. So think of this as the lambda, the diagonal of that lambda matrix that we had here. Okay, so those are the lambdas right here. And then we get a matrix of vectors. So the fitted object $vectors is this 6 by 6, so a p by p matrix where this would be your first eigenvector, second eigenvector, and so forth. And so last time we were interpreting these, and what we said was, look, this first eigenvector is essentially all the same, therefore it's a grand average of all the variables. The second one's going to be a contrast between the first and so combine the first, third, and fourth elements and contrast that with the other measurements and so forth. All right, cool. Well, let's go check the eigen decomposition. So what I told you was, if we look over here, if you take your eigenvectors, multiply that by the eigenvalues, and multiply that by the transpose of the eigenvectors, you ought to get the original matrix back. So let's just go try that. And if we do the multiplication, notice this matches the correlation matrix exactly. So we have just found another way to write that out. But you're probably wondering, why go through all the trouble to decompose it? What good is that? Well, the reason that's good is that we can reduce the dimension while retaining as much information as possible. So let's just say that we were going to drop one of the dimensions. Okay, so drop the last dimension, and notice the eigenvalues here are sorted in order. So that's just like I said on the slide. The amount of variance that we would be losing that we're not able to explain is given by that last eigenvalue. So the amount of variance that we're not explaining is 0.027. So we're only losing 2.7, well, don't call that percent. So you'd have to divide that by 6 to get to percent, since they're, the total variance is 6. But the amount of variance that we'd be losing by ignoring that last dimension is 0.027. All right, so if I were to reconstruct my correlation matrix using only the first 5 dimensions, this is what we get. And what you're going to see is that this is a very good approximation. Okay, we're off in the 3rd decimal point on this next correlation. We're off in the 3rd decimal point a little bit in that next correlation, but this is a very good approximation. In fact, it's the best possible approximation that we could have. That's given by this eigendecomposition. Well, why stop there? Why don't we throw out 2 dimensions? So if we get rid of 2 dimensions, now notice we're going to be sacrificing the sum of those 2 values, but we're going to be capturing the vast majority of the variance in the original correlation matrix. So what you're going to see is that the approximation degrades a bit. Okay, where we tend to be a little bit more off than we were before. Whereas before we hit that correlation right on, now we're off a little bit. We're maybe off a bit more on that third correlation between x1 and x3, but it's still pretty good. And well, we could even go another dimension, toss out another dimension, and this would be the approximation. And so we've done a pretty good job of that. All right, so what I want you to take away from this is that we can decompose our correlation matrix using eigenvalues and eigenvectors, and that provides an approximation if we start throwing out some of our dimensions. All right, now I promised another decomposition. So there's a closely related decomposition called the singular value decomposition. And the singular value decomposition works for non-square matrices. And of course, if it's non-square, it doesn't have to be symmetrical. So in general, if X is just some n by p matrix, and I'm also going to assume that the rank, so the number of linearly independent vectors that form a basis for this X matrix, is R. All right. Then the SVD says there exist these matrices U is an n by R matrix, and V is a p by R matrix, and a diagonal matrix D, such that we can rewrite X as a product of those 3 matrices now. The D's are going to be like our eigenvalues, but we're not going to call them eigenvalues anymore. We're going to call them singular values. Now, there's a very important corollary to this. Remember what I said about X transpose X. I told you that earlier on in the lecture last week. Maybe I should go back and show that to you again. If we go back here, there is some facts about this matrix. And so some facts about this matrix are that if we've mean-centered the columns, then X transpose X divided by the sample size minus 1 gives you the covariance matrix S. And if you standardize your columns, then you get your correlation matrix. All right, so this X transpose X is a very important matrix to us with principal components analysis because we're finding the eigenvalues and the eigenvectors of the correlation of the covariance matrix, which is just this X transpose X divided by n minus 1. All right, so let's go back to SVDs. So with SVDs, here we go. If we take this matrix theorem, the eigenvalues are just the d's squared, so the singular values squared, and the eigenvectors are just v. Now, there's a very easy way to see that. And so if we go back to my notes, let's just compute out x transpose x. So I'm going to write out x transpose. So x transpose is this. When you transpose a product, you reverse the order of the matrices and transpose each of the individual components. This is your x matrix. So where's that coming from? Right here. So if this is x, this is x transpose. Now, sitting in the middle is u transpose u, and we've assumed that u transpose u is the identity matrix. So that's like a giant 1 sitting in the middle of this. Therefore, this is just v times d squared, so d times itself. I got two d's sitting here, and then v transpose. But does this look familiar? And the answer is, well, yeah, it looks exactly like the Eigen decomposition. So these singular values in the d are just the square roots of the eigenvalues, and these v's are the eigenvectors. So another way to think about these the singular values is they're standard deviations, whereas the eigenvalues were telling you the variance in different directions. The singular values tell you the standard deviations, because when you take a square root of a variance, you get a standard deviation. All right. There's another result. We don't really need it, but I'll just mention it. If you were to look at the matrix XX transpose, this matrix, using a similar argument that I had here, would have eigenvectors u and exactly the same eigenvalues. So x transpose x and x transpose share the same set of eigenvalues, but have a different set of eigenvectors. They have to be different because this is the dimensions are different. So this is an n by r, this is a p by r matrix, but they share the same set of eigenvalues. All right, another thing that's kind of interesting to do, I'm just going to post-multiply this SVD by v. And so what we end up with is just x times v is equal to u times the singular values, which I'm going to call y. All right, so the v transpose v's go away, and that's how that happens. Now, remember what I told you last time. How do we get the principal component scores? Well, all we do is we take our x matrix times the eigenvectors, and that gives us our principal component scores. So you can think of the scores as just being u times d, which describe the new coordinates of the points. So when I represent each point in this principal component space, the scores give the coordinates in this new principal component space. All right, so don't lose track of the big idea. The big idea here is that both the eigenvalues and the eigen decomposition in the SVD are helping us find a lower dimensional representation of our x's, and it's optimal in the sense that we lose as little information when we go to that particular lower dimensional representation. So if we wanted to go down to one dimension here, the best one would be to choose this direction, because we could capture as much variance as possible. All right. I want to just walk you through another numerical example. So we've already talked about this example. It was the very first example that we went through in class. So just to show you what that was, I had generated 10 values and made sure that they were correlated. and we found that the first eigenvector was 1, 1. Second eigenvector was 1, minus 1. All right, well, let's go take a look at that. And I got to go find that page again. There we go. We're going to try out the SVD. Here's our SVD. So I'm going to go compute the SVD of this simple tiny data set with 10 rows, 2 columns. And so what does the SVD object look like? Well, we have our singular values. Then we have the U matrix and the V matrix. Notice the V matrix has the eigenvectors we found earlier. So this is something actually slightly strange to me is why these aren't exactly equal. They should be exactly equal. And this essentially is the line 1, 1. All right. So let's just go try the SVD out. I said that if we took our U matrix, multiplied it by the singular values as a diagonal matrix, and then multiplied that by the transpose of the V's, we'd get the original data back. And sure enough, we do. So this matrix down here equals this matrix up here. So we've confirmed that the SVD works numerically. Well, let's now go do an approximation. So if I were to drop one of my dimensions, in this case I can only drop one, what we end up with is an approximation. Here is that approximation to the original matrix. One more thing, I said that we could compute scores by just taking the U matrix times our singular values. And notice this is exactly what PRComp gives as the scores. And there's a reason for that. PRComp uses the SVD function to get us the scores. All right, so what you should take away from this is this big idea that this singular value decomposition is going to help us find lower dimensional representation of a matrix in an optimal way. All right, so optimal in the sense of principal components analysis. All right, so I gave you a couple really small homework problems this week that ask you to just reproduce a matrix using SVD and the Eigen decomposition function, just to give you some practice on this. Okay, good luck.